Hello everyone. Today we have a very important lecture about Black-Scholes model, and it's not only formula Black-Scholes, it's the model, because you remember that our great aim in this course is to model financial market, and it means that we should model stock prices and to define prices for derivatives. So, I would like to recall you facts from previous lectures. Um, you remember that for modeling stock prices, because stock prices are very fluctuated at any given moment, it just balance between support and forget. Um, so we consider it the stock prices as stochastic process, and we would like to model it using Brownian motion, demand and supply. So, what is Brownian motion? Brownian motion, you remember that it's continuous stochastic process, and that this process has several main properties. The first properties it is that the value of this process is initial time is zero. The second, that the all trajectory, all path of this process is almost surely continuous, and it means that its trajectories without jumps, sorry. And property number three, it is that the linear process has independent increments. Increments. Do you understand what is increments? Increments, it is the difference between between two values of this process. So this process has independent increments, and more than this, um, increments has Gaussian law of probability, Gaussian distribution. So it denoted by n, and the mean of this distribution is 0, and the variance t minus s. It is the difference between two times. Two times. There are another properties, there are another definition of, for example, we can define the Brownian motion as a Levi process, for example, but it doesn't matter. The first fact that you should remember, it is what is Brownian motion. The second fact is Ita lemma. What is Ita lemma? Ita lemma is a rule how we can differentiate the function from stochastic process. So if we have stochastic process and we can write it in this algebraic form, because it called eta process, because I see the mistake after a we should write dt. Dt. So you should, that x is stochastic process or diffusion process, we can say it, and on the left side you see dx, so it is as a differential on stochastic process. But on the right side you see two terms. The first is the function r, its function which depends on x it is this process, and t its time, and dt. plus function b, and b depends on x and t2, and you see dz. Um, so if 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 you would like to consider on the equals a dt, it is ordinary stochastic equation. But if we have this term, it is stochastic differential equation, and and stochastic differential equation requires stochastic calculation. Stochastic calculation. Um, and this function we can call trend function or shift function, but this function it is diffusion coefficient. Um, so, for example, we have this stochastic process, and we have a function g. It is non-random function. Mm, it should be differentiable, and so this belongs to this class and continuous function, and we would like to find dg, yes, but g depends from t and from x from t. It is as chain rules. It is as if you would like to find differential from a complex function, compound function. Maybe. No, in English terms, it is a chain rule. Chain rule. Uh, so how we can find dg? The answer on this question gives Ito's lemma. Ito's lemma. Dg equals um, some function multiplied dt plus this function multiplied b dz. A, b we take from this, but these values we can find if we know the form of g expression. For example, g is t square plus x square, so we can find dg respect to dx. It's 2t plus 2x, yes, and multiplied by a. What is and after that we can find dg respect to dt plus this, and I think it's easy. And on the previous lecture we did this, and I explained this in more detail. So let's move on. On the previous lectures, we derived the Black-Scholes formula as a formula pair price and as a discounted mathematical expectation. So we know this formula, but this formula um, was obtained after Black-Scholes theory as a more easy variant of getting of obtaining this formula. Okay, but today we would like derive the Black-Scholes equation and Black-Scholes formula um, as as they did Black and Scholes. So let S is the price of the stock, T a time 2 years. So if it is 3 months, it's 1 divided by 4 in years. Yes, and let us f from SET the price of derivatives as a function of time and stock price. It means that it's the Payot function. Payot function. You know how we can write the Payot function for call option. Please, who would like to say? Vika.
As I remember, it's S minus K and 0, and we choose the maximum of these two values.
Yes, you're right. Well done. Thank you. So I repeat, f it's for your function. So if we have this market price of stocks, and if we have strike price of, for example, call option, the difference between S and K, it's for your function. If S more than K, but if S less than K, so it's just zero, because we have obligation to exercise this option. The price of underlying asset, in our case it is a stock, follows a geometric Brownian motion. Geometrical Brownian motion, it means that in eta process, this coefficient between dt is in this formula, coefficient a from x and t before dt. It is mu multiplied s, and coefficient before dz, it is sigma multiplied z, where mu and s, mu and sigma are constant value. But s, it is a stochastic process, and it depends on time and on random. So Formula 1, it's geometric Brownian motion. The payoff of option at maturity is known, and I recalled you that f from SAT, it's difference between s and constant k, and its maximum value. To find its value at an yes, we need to use eta lemma. So formula 2, it's just formula when we use lemma eta to equation 1. So we have ds, and we have function gsf. We don't use now that it is different. We only write f. So we use lemma eta, it is this, and we write a from our equation. All of these are the same, only a and b we write from equation 1. Yes, only a it's mu multiplied s, b it's sigma square s square, and everything is the same. After that, we would like to discretize the equations for the s. So equation 1 we rewrite, and instead ds we write delta s, you see, and instead dt we write delta t, and instead delta and instead delta z we write delta z. And formula 2 we rewrite 2, and similar we write instead delta f df delta f, and we replace dt delta t and z delta z. Yes, you see, it's easy. Yes, it's easy. And what's our idea now? We see that the chance, random, stochastic, there is only in delta z, because z is winner process, because mu s constant, delta t it's not a random value, sigma s constant, and only delta z in the equation 3 and in the equation 4 is random value, is stochastic process. And our idea is maybe we can to add this equation or to distract this equation, or to multiply this equation, or to find a linear combination of this equation in that way that that result will be without delta z. Do you understand idea? So what do you say? What do you think? How we can, what operation we can use that delta z disappear, in order that delta z disappear? Maybe sigma s, it's the same. You see, it's the same. Maybe if we 3 multiplied by Vika, what do you think?
We can write the equation as delta s minus mu s delta t, it's equal sigma s delta z.
If we
So sigma s delta z equals delta s minus mu s delta t, and write it in delta f equation.
You think that we can express this?
Yes,
and
yes.
multiply it in this, and after that it will be with express delta z from 3, yes,
From yes, and
delta
then
z and substitute in 4,
yes.
and it will be without. No, yes, you're right. Or it is the same if we multiplied 3 by this ratio, yes, no, from minus, for example, and find the sum, 3 and 4, no, plus, yes. And how we can do this? For this, I need to give you definition of portfolio. Portfolio is a vector that consists of amount of assets. In common cases, it is this vector theta 1, theta 2, theta n, where theta 1 is amount. So, for example, theta 1 is 3, and its amount of stock price named Facebook. Theta 2, for example, is amount of stock price named, I don't know, Google, and so on. Yes, and if we know this amount, so the value of portfolio we can calculate as sum of products. It is its amount, for example, 3 shares or 3,000 shares, and multiplied by price of these shares, plus multiplied the amount of another shares, multiplies another price, yes, and so on. So it called value of portfolio. For example, if we have portfolio only of 2 papers, so the value of this portfolio equals the amount of stock price or kind one multiplied multiplied price. No, so it's amount multiplied price, amount multiplied price, and sum of these products. And and in order to do this combination between 3 and 4, um, we should construct a portfolio with amount minus 1, and the second amount it's the df respect to ds, because we can find this and it will be constant, so it's amount. Uh, and and let minus 1, it is a short position, um, and its amount of amount of options. And this is because it's with minus, yes, with minus it is a short position, so it is we sell and forget, so it's short position. But it's with sign plus and it's long position. It's we buy and we wait. We buy and we wait. So it is portfolio, and let the initial price or current price of option F, and price of stock S. S. S we know, but F we don't know, and we would like to find today in this lecture this exactly this F. So the value of this portfolio is amount multiplied price, so minus 1 multiplied F, it's minus F, plus the amount df to respect ds multiplied s, right, s. So 5 is the value of portfolio. After that, we would like to take a time period t plus delta t, and formula 5 we can rewrite in discrete form. It is instead p delta p, instead f delta f, and s replaced by delta s. And we remember very important formula that increments of Wiener process we can write as epsilon multiplied by square root from delta t, where epsilon is white noise. It is process with independent increments, and uh, distribution is normal with mean 0 and variance 1. So it's very important that in formula 6 we can replace delta in formula 6 in 3 and 4 in this formula. Yes. Uh-huh. So we substitute 3 and 4 into the expression 6. So you see expression 6, yes? Delta f, it is form, and delta s, it is 3. And if we substitute this, we get the next expression. So after it's easy to obtain, and after this lecture, you should to write a test, and in this test, it is the task is to get formula 7 maybe. So substitute 3 and 4 into expression 6. Yes, it's easy. Delta F we have, delta S we have, and multiplied the df respect to ds. What we discuss after that? And you see that in the 7, um, delta z term has vanished, disappeared. Yes. Um, so uncertainty has been eliminated, and the portfolio is riskless, effectively riskless, because we haven't the stochastic term. We haven't only time, only constant, and so on. The rate of return on this portfolio must be equal to the rate of return on any other risk instrument. Um, why? Because otherwise there won't be opportunities for arbitrage. And before we were speaking that it's efficient market hypothesis, that in average it doesn't matter if or we buy stocks or we deposit money, the profit is zero in any case. The profit is the same, no zero if I compare the deposit and the buying of stocks. The profit is the same. So now assuming that the risk-free rate of return is R a little, and we can write this that the change of portfolio is equals R P delta T. What does it mean? It means if we deposit the value of portfolio P with interest rate R, and during the time delta T. Yes, it's formula. From this equation we can get the formula. Um, so um, so we have two formula for delta P. It's formula 7 and it's formula 8. This delta P, yes, and you see that this delta P2. So we can write that this part in the right side equals this part in the right side of formula 8. And you see that this delta T and this delta T, and we crossed this, yes? So we have this formula. In left side it is this, and in right side, uh, uh, um, RP del RP delta t, delta T, and P equals is formula 5, yes, minus F plus the respect to ds, but we multiplied by minus 1 because it's with minus, and it's more convenient if it will be with plus left side and right side, so we change these terms. And we cross this delta t, yes, and After several manipulation, it's easy. You see that it's RF on the right side, and R multiplied this. We move on the left side, and these two terms on the left side too. So with the assumption of the Black-Scholes model, the second order partial differential equation holds for any type of option as long as its price function f is quite differentiable with respect to s and with respect to t. Um, so it's a well-known, celebrated Black-Scholes equation, and you see that it's not a stochastic equation. It's only partial differential equation. And how we can solve this? Um, we can solve this equation only if we have a boundary and initial condition. Um, in a common case, this equation can be solved numerically using standard method of numerical analysis. For example, finite difference method. But we would like to get analytical solution. Um, so we recall again that f is for your function, and for us it's a boundary condition, and its maximum value between this difference s minus k and 0 as market price, k it is strike price. So if market price more than k, we win. If less, we lose. And for put option, situation is opposite, and for your function, it's maximum between this expression and 0, and this it is different between k and s. In this case, s and k, but in this it is k minus s. And now we would like solve the Black-Scholes equation to diffusion equation, because how to solve the diffusion equation, it is a well-known problem. For this, we write the expression 9. What is expression 9? This expression 9, but we would like to write this, and we would like to write df respect to dt only as f respect to t in this form. It doesn't matter, but we would like. So this it will be f in this form, and so on. So expression 9, it will be you see uh, f differential f to respect t on the left side, and all other terms we move to the right side. So this is expression 9, only in another form. And let's denote f from t capital and s as function h from s. Because T capital, it is constant, it is time to maturity, time to exercise option, and it's constant. Um, to solve 9, we recognize that it is Euler equation, which can be transformed into diffusion equation, and we would like to transform in diffusion equation, and for this we introduce the change of variable transformation. What does it mean? It means that we denote y as logarithm s. So h from s is h from e to the power y. It's uh, 2 point, no, exponent, and we introduce town as t capital minus t little, and if t capital is constant, t little it is current time. So function from t and s, we can write as a function, another function g from town and y. If you ask me why its transformation, it is a change of it is a well-known change variable transformation after after reducing this equation of this form to diffusion equation. So we have that df respect to dt, yes, it's f in the left side, and we would like to find a differential. So it is this, but why with minus? Because because minus in this, because it is as no, chain rule. D G respect d town multiplied d town respect to dt. Yes, so it is minus. And similar df respect ds, where we have s in y. Yes, only in y. Town doesn't contain s, so it is dg respect dy, and dy respect dz. It is we should find derivative of ln s, and x1 divided by s. Yes, it's clear. After that, we can find the second derivatives, because you see that this equation contains the second derivatives. So the second derivatives from this, it will be the second derivatives, and multiplied by derivatives from 1 divided by s, uh, and minus no, because it is product, yes. So derivative this multiplied to this plus derivatives from 1s multiplied this. Um, and now we should substitute them into the expression 10. In expression 10, so we substitute instead this expression, and instead this, so all this, all that we found to be substitute in 10, and the initial value we substitute to initial value will is this f from ts equals h from s, and in this case it like this. it looks like this. Rewrite the expression in another variables. For this, we denote A as sigma squared divided by 2, B as R minus sigma squared divided by 2, and C as minus R. And rewrite this in this form. Why? Why? Because we would like to have only the second derivative, the first derivatives respect to y, and before only coefficient. So all these coefficients we denote one letter. Yes. So you see that this form is more convenient than this. The next change of variable transformation is that, and it's well-known transformation, and maybe you can know this from course um, method um, method of equation of mathematical physics. Yes, you remember this course. So to solve 11, we use the solution of the Cauchy problem for the diffusion equation. So we would like that it will be u derivatives from this u capital respect to t, but in the right side the second derivative. So now we should to find this and to check if it's true. So we find these three derivatives: du respect to the town, and u is in this form, and we would like to find derivatives respect to town, but town is in the power, and town is as argument of this function. So it is derivatives, the first term multiplies the second plus this term multiplied derivatives from this. So derivatives for this, it will be exponent multiplied by derivatives from this power, and power respect to t, it will be only alpha, and multiplied this function d, plus the first term we only rewrite and multiplied by derivatives from v. And similar, we can write these derivatives and the second derivatives. Yes. After that, we denote lambda in this form. So this and this we denote as lambda, and substitute all this in the expression 12. In the expression 12, and it's only for defining A, B, and C. So we comparing the resulting equation with 11, we find, so you see this 11, yes, this A, B, and C. A before the second derivatives, B before the first derivatives, and C before G. So lambda before second derivatives, so it's A. 2 lambda B before the first derivatives, but in this equation it's b, yes, before the first derivatives. So comparing this, we write this system, and after substituting lambda into the expression 12, we receive the diffusion equation for the Black-Scholes uh, partition differential equation. It is u derivatives respect to tau equals 1 second sigma square the second derivatives u respect 2 times respect to y, and this is initial condition. It is from 12, from 12. From 12 because we found lambda, and so we write this because lambda x r and r x 1 second sigma square. But how to solve this equation? It's another problem, and it is a very technical, difficult problem, and we can solve this using the standard convolution method. It is using Green formula, and maybe you remember this from equation of mathematical physics. Maybe you don't remember, I don't know. Um, so, using standard convolution method and initial values, we have that solution of this we can write in the form u from white and t equals this coefficient integral and function h, and multiplied e to the power you see dz, and we can rewrite this um, as 2 only in the denominator. Yes, we can this rewrite, and it will be sigma square root from 2 pt. And you see that it is like normal distribution, and but after some manipulation, we can get a Black-Scholes formula. A Black-Scholes formula in the form in this form. So if we know initial price, if we know strike price, and if we know interest rate and volatility, we can compute D1, D2. After that, find normal distribution from D1, D2, and calculate the fair price of call option. How we can find, for example, sigma from historical data? I will tell you later. I'm sorry, just a moment.